How we doing? Welcome back. Today on the bench we got the legendary Octaxe Gamma 8 BM1370 chips. This particular version, this is the 6-phase, 6 CSD version designed for approximately 12 terahash. The Octaxe has been around for quite a while, about a year and a half roughly, I think, at this point. It started with a little different design for the phases of the CSDs. They actually ran, I think, four phases up and down up here by the fan connectors. It's really hard to show you on my microscope, but ultimately they would run the CSDs up and down over here. There was 4 of them, I believe. So you had the whole power circuit was on this side that fed down. In this case, what they've done, I mean, rightfully so, they've spread them out across. Let me get this a little bit better in view here for you guys. But they've spread them out across here to try and do 2 things. This is a parallel circuit. So each CSD we add, we cut down the individual current load on each CSD. And in turn, we cut back. We distribute the heat better. And hopefully we see less failures. Okay? CSDs are essentially MOSFETs. And unfortunately, in my experience, you know, MOSFETs are prone to failure. I mean, I've seen some designs better than others that last a lot longer. You see things like on the BitAxe with the TPS design, that seems to hold up really well. But this TI designed ASIC power supply doesn't seem to hold up as well. So there's a lot of speculation as to why, but at the end of the day, it's the most common failure on all these Nerd devices. So, you know, the only thing, and I tell this to every customer every time they ask me, what can I do to better prevent this? And the only thing I can suggest is control heat. That's the biggest thing, is control heat. Technically, these CSDs are designed to carry much more current than these devices push to them. We don't see that, you know. We see a lot of failures with them. I don't think current's the issue necessarily, but controlling heat is probably the best advice I can give you. You see the devices that we have back here. So both of these ones here use CSD circuits. That device has been running on and off since September, October of last year. And that one here has been running for a year and a half. Never had a CSD failure. So it's not that they all fail. It's, you know, it's hit and miss. It's just whether it's quality, whether it's circuit design, whether it's manufactured. I couldn't tell you. I don't want to speculate. I'm not sure, but that's the biggest difference here is we have 6 phases. We have 6 CSDs on this board design. Again, designed to break up the current, break up the heat, and try to have longevity in the components. So, all right. Well, we're gonna break this down and figure out. We'll do a visual inspection and we'll take a look at all the components on here. See if we see anything burn visually. We'll check for shorts. We'll do what we got to do, and then we'll go to some voltage injection. See if we can find our problem. All right, we're back. All right, so let's do a quick visual inspection here. Pan connectors. CSDs, coils, not sure. It's interesting. No writing on these coils at all. And the caps aren't on straight. That's interesting. I don't see any visually cracked. When I see things like this, I just look close to make sure. But most of this is flux. This is flux from the solder paste coming over the top. Okay. Let's check our ASIC chips to make sure we don't have any cracks. Those are scratches, not cracks. That's exactly what that is. Again, scratches. scratches. Scratch. This is actually the silicon contact. That's what we're looking at here. Okay, I don't see any cracks. Everything looks pretty good. Okay. I see that they got the heat sinks stuck to the backside of the V-REGS. I see all of the capacitors here. Okay. Crystal. Everything looks pretty good visually. Everything looks pretty good. Okay. So let's take a look at the Let's take a look and see if we got a short. And we do. So positive to, I went to the bottom side of the, here, I'll show you where I'm going here. So power comes in through the top side of this fuse and travels through the fuse out the bottom to the circuit. So I want to be on the circuit side, bypasses the fuse, so coming in here at the top. And I'm using the negative on the XT60 connectors, negative, and I have 0.2 ohms. So that's a short on the board all day long. Now let's see if we can find out where it is. So we're going to go over to voltage injection, and we're going to bring in our thermal camera. All right. So I'm doing 6.5 volts, 4 amps. I'm going to go to negative on the XT60 connector. And as somebody pointed out in one of the comments, and they're absolutely correct, is I'm going to take the positive to the back side of the coil. And I'm going to do that because I want the current to flow from connector to coil and not go through the ASICs, honestly. I've never had an issue, but it's a safer way to go. Let's isolate the circuit to just the components between the two, and then it's safer ultimately for the device. So that's what we're going to do. So negative side or back side of the coil, I'm drawing 4 amps, and I'm looking in the thermal camera. I'm looking for a heat spot in the thermal camera. After doing some voltage injection, I think we've identified the V-REG that, as we've shown before in other videos, but we've identified the V-REG that is tube lane, causing our short. So we're going to go ahead and we're going to get the board onto the board heater. We're going to heat it up to 400 C. It's going to take about 10 minutes roughly for the heater to heat up enough, that radiant infrared heat to pass into the board and for the board to soak it up. So we're going to give it about 10 minutes and then we'll be back. All right, we've got the V-REG removed. Apologize, my battery decided to die suddenly. So I didn't get to film that part of it, but let's go ahead and switch over here. Give you guys a little bit better view. So V-REG's off. I'm going to add some lower melting point lead-free solder paste. Grab ourselves a new V-REG. I did validate that the short was gone after I removed that V-REG. Always good. There is 6 of these. Could be more than one failure. Not that I've seen that happen. I've had one fail, powered up the board, and had a second one fail right after it. But that's only happened one time. Okay, dot to the lower left. This thing's set up where it needs to go. All right, now let's get some heat on it. And we're looking for that V-REG to drop, just like that. Oop, squared itself right up. Let me give it heat for a couple more seconds here. All right, looks good. Hot plate off, so the board can start to cool. There's our guy. All right, a little bit of flux. Soldering iron on. Another beautiful Sunday. Working on Bitcoin miners. Always a blast. And we're almost at temp here. Clean and tin my tip. And then let's get in here and that looks good. Okay. I like to kind of scoop up on these as I'm doing them to make sure that we get good pin contact. The sides of the pins come out the side of the chip. Unlike ASICs, they actually come out the side of the chip, so you can get good pin contact with solder. No bridges though. All right, that looks good. Let that cool down for a minute here. Turn that off. Yeah, the CSD failure is definitely the #1 failure on all of these devices. It's unfortunate, but it definitely is the case. And as I've mentioned before, the best thing you can do as an owner is just control heat as much as possible. So run a shroud that directs more airflow down. They are rated for higher heat than what these miners typically run at, but it's the best advice that I can give people when they ask me. It's just do your best to control the heat. Other than that, a lot of the longevity really comes down to circuit design and to proper tuning of the CSDs to the board, which unfortunately doesn't happen a lot. And that tuning for every single board design, I mean, if you just took the plans and you just copied it and said, I'm going to make my own, and then you need to properly tune all the snubbers for the CSDs to try and get the best life out of them. That would be the technically the best thing that you can do for them. Texas Instruments will show you in their breakdown of this circuit. They'll give you all the snubber values, but they will also tell you that those are for sample only. And the best thing to do is to tune the snubber values with an oscilloscope to your physical board. And that is not something a normal person can do. That doesn't have an oscilloscope. It's something the manufacturers who design their versions, I'm going to call it their versions of these boards, to try and help. Is it the perfect fit, end all, solve all the problems? I would say no. Does it dramatically reduce the number of failures? Yeah. So what we did on the QX is we tuned it, had it tuned, I should say, to our board design, to our layer thickness, to our components that we used, and it dramatically helped. Unfortunately, not everybody does that. So, all right, now let's double check to make sure that our short is gone. I'm going right to the XT connector, bottom of the fuse. Yep, looking good. 2.9K ohms and climbing. So we're going to pull this board off the heater. We're going to let it naturally cool. We're not going to accelerate cooling because it'll promote cracking of chips. We do not want that. So we're going to let it cool on the bench or on the silicone pad for about probably the next 5 minutes, and then we'll be back. All right, board is cooled down. Set it to the side for a second. I'm going to prep. I got 2 XP90s here that I keep ready to go. We're going to put on the perfect amount of thermal paste. This is how I put the heat sinks back on Octaxes, okay? Heat sinks down, face down on the table. I come in from the back side and I line up the bolt holes for both heat sinks. I start my screws. This particular board, I don't have the customer's heat sinks. They didn't ship them with them. So I don't know if he has spacers or not. We don't use spacers on our products because of certain manufacturing variances and things to that effect. I see probably more issues with spacers than without them. You know, if you change your heatsink out, spacers aren't going to do you any good because of the changes in dimensions. I run these down with just my fingertips. And then I do the second heatsink. Okay, so then I pick it up and I look at all 8 screws, and I'm looking at the length of the screw that's coming through the bracket. And I'm going to tighten them with just my fingertips. Okay, I'm just twisting with my fingertips. And I want the screws to be the same length. Now, here's a good example. On this heat sink, the right screw is down a little further than the left screw. So I'm going to back out the right screw a little bit. I want balanced pressure. I'm going to tighten up the left screw a little bit. And so I have the same length of screw coming through. And I've got decent tension. I'm not trying to reef these things down. Over tightening, like I said before, can cause problems. I'm watching the board. I'm looking for the board. I can see right through between the board and the heatsink. I'm seeing balanced contact, but I'm also making sure that I'm not flexing the board. I want to, just as it starts to flex, we want to stop. We do not want a lot of flex in the board. This screw, yep. I'm onto the second heatsink. Actually, I can see all the way through to the second heatsink. I'm looking for the same thing. I'm looking for the same length of screw through the bracket. That's what I'm looking for. On right and left sides. Top and bottom. Perfect. And that's it. I just use my fingertips. That's it. Doesn't need to be any tighter than that. I've got good contact. You don't need to reef them down. Now we're going to put the fans on. We're going to pop on our display. That's my Octaxe display. Okay, I'm going to fire it up. Okay, fans coming on, display powered on. Change my view on this side to the PC so I can see the dashboard. And I see it is drawing 205 watts, 12.1 volts. My ASIC temperature is at 42.2, and my VR temperature is at 32.9. This is what we want to see, 208 watts. That tells me that we've got all 8 ASICs firing. That looks good. It is set to, this is the Bitronix firmware version that I use on these 6 phases. So it's the older dashboard, but I'm running 700 megahertz and 100, what is that? 1120, let's see what they are running on here. So the 700 1210 is the firmware, is the frequency and voltage that is set on these. It's hashing at 11348. Let's see if we can get that in their screen here for you. 11424. Expected 11424. So 11464. Yeah. So we're right at target, which is great. I'm going to let this run. Now, this typically has a rear fan on it. This is usually mounted to a stand with dual rear fans. At this frequency and voltage, I expect that temperature is going to be somewhat difficult to control. It's going to continue to climb until it gets to that point. This is set at 100% fans. I think this is how they ship them. So I'm gonna watch it pretty close just to make sure that we're not getting too hot. But I want to make sure that the device is working the way we expect it to. So it's using 17.56 amps, 212.8 watts, and it's at 53.8 on the ASICs and 48.6 on the V-REGS. And I didn't even remount the rear heat sinks back on it yet. So it's cranking away. I'm going to let it hash and then we'll get it buttoned up, but it's another Octaxe fixed. Yeah, not bad. Again, we've talked a lot about the CSDs and the failures and troubleshooting these devices. Wanted to share the journey with an Octaxe. It's starting to become more commonplace in my shop, and that's okay. We're here to fix them for you. If you need repairs, ixtech.xyz, very top of the website. Click on repairs, fill out a form, pay you $25, send it in, and I'll take a look at it. If you're lucky, I'll throw it on a video. Thanks for watching. See ya.